Yes, good afternoon. Good afternoon, guys. Welcome to the 28th lecture of fluid mechanics. We are in the unit 3. The topic name is turbulence and laminar flows. All right. So, in the unit 2, we have discussed about the classification of types of flows. That you are having steady flow, unsteady flow, constant flow, non-constant flow, laminar flow, turbulent flow, rotational flow, irrotational flow. Like this, you are having 6 various types of flows. Now, in this unit, you are completely studying about what are the characteristics of laminar flow, what are the forces acting on the laminar flow, right? Perpendicularly, parallelly, what are the losses in the pipes, and also what are the characteristics of turbulence flow, how they are acting according to the Reynolds number, what are the minor losses in the pipes, it may be in the open pipe or in the closed pipes. We will see all these unit topics in this unit 3, right? So today in this class we'll discuss about the various characteristics of laminar and turbulent flows. So in the last class we have discussed about the introduction of the introduction of the laminar flow and turbulent flow. Okay, so today in this class we'll discuss about the Reynolds experiments, how the Reynolds has derived an experiment. Based upon the experiment, he made a formula which are useful for turbulent flow problems, and what are the characteristics of the laminar and turbulent flows. So we'll see these topics in this class. Okay. Yes, the figure depicts here how the oil is flowing in the pipelines in an oil and refinery company. So this oil refinery company located in the Gulf countries, or where the seashore is available, where the crude oil is, we are getting. So in these pipelines, we are having the crude oil in the form of liquid content flowing in these pipes, right, for refineries. So how the flow is taking place, how the reaction flows whenever the fluid is flowing in the bent pipes, when it is flowing in the T sections. It's like this you are having in the companies and factories, right? Now, if you see the Reynolds classification according to the motion of fluid, we are having 3 types of classification. As I already mentioned, what is this one? The first one is Reynolds classified the flow of type according to the motion of the fluid. So whenever we are sending a high viscous fluid in a water container, so with a low discharge from top to bottom or from horizontal through some mechanism, the water is flowing in a straight line fashion. The water is flowing in a straight line fashion. So whenever the water is flowing in a straight line fashion with a low discharge, see here, the fluid is flowing in a straight line without any disturbances. So this type of flow is nothing but a laminar flow. Every fluid molecule is followed by the straight line path that was parallel to the boundaries of the tube. So if this is a tube, the tube anukunte, right? So this is a boundary of a tube, circular tube. Okay, if this is a boundary of circular tube, the path of the fluid is parallel to the boundaries of the tube, and every molecule is facing towards the one straight side. Then this type is known as laminar flow type. Okay, second one. Whenever the liquid, whenever the oil or liquid is flowing in a container, whenever this fluid is moving with a medium discharge, thereby the flow will be in a some wavy nature, that is formed in the wavy nature. This type of flow is nothing but a transitional flow. Every fluid molecule followed by the wavy but parallel path that was not parallel to the boundaries of the tube. So this wavy nature of the fluid is having some wavy nature, but this wavy nature of the fluid is parallel to the other layer of the wavy nature of the fluid, but these layers are not parallel to the boundaries of the tube. Then that type of tube you are calling them as transitional flow with a medium discharge. Got it? Next. Okay, only two persons. Next, third one. Third one is the high discharge. Okay, so whenever the fluid is going, the same thing, whenever the high discharge we are flowing the oil in the container, whenever whenever these molecules are taking in a very complex and difficult path, that type of flow is nothing but the turbulent flow. Is nothing but the turbulent flow. Every fluid molecule followed every complex path that leads to the mixing of the dye. సో అప్పుడు ఏం జరుగుతుంది, వెన్ ఎవర్ హై డిశ్చార్జ్ జరిగినప్పుడు వాటర్ లోపల డై మిక్స్ అయిపోయి ఇట్ ఈస్ గోయింగ్ ఇన్ డిఫరెంట్ డైరెక్షన్స్ విచ్ ఆర్ నాట్ అట్ ఆల్ ప్యారలల్ టు ద boundary flow. Then that type of flows we are calling them as a turbulent flow. Then the value of Re determined by the type of flow experiment tubes, we are considering Re is less than 1000 number unte, then we are calling this as a laminar flow. When R is in between 1000 to 2000 number, then this type of flow is nothing but transitional flow. When Re is above 2000, when Re is more than 2000, we are calling them as turbulent flow. Is calling them as a turbulent. So as already we know that Re is equals to U into 2 divided by V. There we have cancelled rho by rho, therefore U into D divided by V. Then according to the Reynolds number, the transition from laminar flow to the turbulent flow depends on what? Depends upon the geometry, depends upon the surface roughness, depends upon the flow velocity, depends upon the surface temperature, and depends upon the what type of fluid we are dumping into the container. So laminar flow నుంచి turbulent flow కి చేంజ్ అవుతున్న సమయంలో, అంటే ట్రాన్స్ఫర్మేషన్ జరుగుతున్న టైంలో, it depends on what type of fluid you are using, the temperature of the fluid, and the velocity of the fluid, and the surface roughness with respect to the boundary layer of the pipe, and also the geometry of the pipe. So any reasons though, the dye or the fluid is converting from laminar flow to the turbulent flow. Next, the flow regime depends mainly on the ratio of internal inertia forces to the viscous force. Therefore, the Reynolds number Re is equals to inertial force by viscous force. That is equal to V average D by V. That is equals to rho into V average D by mu. At large Reynolds numbers, the initial forces, which are now proportional to the fluid density and the square of the fluid velocity, are large relative to the viscous forces, and thus the viscous forces can't prevent the random and rapid fluctuations of the fluid. That is turbulent. At small or moderate Reynolds number, the viscous forces are large enough to suppress these fluctuations and to keep the fluid in line. This type of thing is known as laminar flow. Next, for the flow through the non-circular pipes, whenever the fluid is flowing not in the circular pipes, the Reynolds number is based on hydraulic diameter. Circular pipes flow అవుతున్నప్పుడు, that is one type of thing. Whenever the fluid is not flowing in a circular pipe, then Reynolds number is based upon hydraulic diameter. Then hydraulic diameter of various non-circular channels are shown here. Okay, see here. So for the circular tube, the hydraulic diameter is 4 into pi into d square by 4 divided by pi into d. So pi d cancel చేసుకొని 4 cancel చేస్తే only 1d is remaining. Next, what is the square duct? dh is equal to 4a square by 4a. Cancellation చేస్తే మనకి a వస్తుంది. The rectangular duct dh is equals to 4ab by 2 of a plus b చేస్తే 2ab by a plus b. Then open channel తీసుకున్నప్పుడు dh is equal to 4ab by 2a plus b. So these are the various formulas for the non-circular tubes by using the hydraulic diameter. Okay. So the figure also depicts here, whenever the fluid is injecting at one corner of this pipe, so whenever the velocity is flowing average, so the dye is injected at one point is flowing in zigzag way initially, and it is taking the action of laminar flow going straight and again it is converting into the turbulent motion. Okay, then these are related to the fluids. ఇప్పుడు వరకు మనం experiment చేసింది fluids మీద. Now if you see the experiment related to the gas, see here how the laminar and turbulent flow you can see. So if you see the laminar flow, initially from the flame, from the fire, so it is moving in the form of a straight line. It is moving in the form of a straight line slowly. At certain point it is changing the orientation and it is transforming into directly into the turbulent instead of transitional. Transitional kaakunda directly it is converting in the stage of turbulent flow. It's going in the form of turbulent flow. Then if you see how the reaction takes place, the laminar is a smooth streamline, smooth streamlines and highly ordered form. So here the laminar flow ఎలా ఉంటుంది, it is a highly ordered motion లో ఉంటుంది, whereas a turbulent is having the velocity fluctuations. ఈ ఫ్లక్చుయేషన్ జరిగినప్పుడే తక్కువ ఉందనుకోండి తక్కువ చూపిస్తుంది, ఫ్లేమ్ the direction ఎక్కువ ఉన్నప్పుడు the rotation will be changing. Therefore there is a velocity fluctuations and highly disordered motion. Laminar వచ్చేసి ordered motion, turbulence వచ్చేసి disordered motion. And transition ఏంటి, it is located in between the laminar flow and the turbulent flow. The flow between the laminar and turbulent flow is nothing but a transition. So ఇది మీకు ఈ concept throughout the end of the syllabus you have to keep in mind what is the laminar, what is the turbulent, what is the transitional. Okay, most flows encountered in the practice are turbulent. So general గా మనం ఇవి experimental లో కరెక్ట్ గా కాన్స్టెంట్ వెలాసిటీ, రైట్, లో డిశ్చార్జ్, మీడియం డిశ్చార్జ్ కరెక్ట్ గా చేస్తూ పోతే experimental లో we can see all the laminar, transitional and turbulent. But whenever practical ga, for example మీరు if you are going for a bath, ట్యాప్ తిప్పారు అనుకోండి, సో ట్యాప్ తిప్పుతున్నప్పుడు వాటర్ లోపల పడుతుంది బకెట్లో. సో whenever it is taking practically it's nothing but the turbulent. మీకు ఎక్కడ లామినర్ నుంచి ట్రాన్సిషన్ నుంచి turbulent కనబడదు. So whenever you are filling the water in your water bottle in a college, వాటర్ ట్యాంక్ లో నుంచి your water basin లో నుంచి you are filling the water in your water bottle, it is also a type of turbulent flow. Whenever you are drinking water through your mouth with the bottle, it is also a turbulent flow. So whatever the practical things you are seeing in your day-to-day life, these are all turbulent type. Okay, next, laminar and turbulent flow behaves. Laminar and turbulent flow behaves depends upon what? Depends upon the parameters. What are the parameters? The velocity of the gas, okay, the physical shape of the boundary, physical shape of the container. So like this you are having other factors to be considered, right? So this is example of the gaseous form, this is example of the liquid form. So దీనిలో ఏం చేస్తున్నామంటే ఒక పైప్ లో ఒక కంటైనర్ క్లోజ్డ్ సర్క్యులర్ పైప్ లోపల వాటర్ ఉంది, వాటర్ లోపల వీఆర్ పంపింగ్ ఎ డై ఇన్సైడ్ ద వాటర్. మీకు డిఫరెన్స్ కనబడడానికి ఈ ఎక్స్పెరిమెంట్ అనేది చేశారు. ఓకే, సో see the laminar flow when the dye is flowing into this pipe and flowing in a straight line fashion. Whenever it is flowing in this pipe and is flowing in a zigzag way, this is nothing but the turbulent motion, right? Now, so if you take a simple example of this transition of this types of flow, see the question. Given two pipes, one with a diameter of 10 centimeter, other with a diameter of 1 meter. So రెండు pipes ఉన్నాయి, one pipe diameter వచ్చేసి 10 centimeter, other pipe diameter వచ్చేసి 1 meter. And what velocities will the flows in each pipe become turbulent? What are you saying here? At what velocities will the flows in each pipe become turbulent? So ఏ velocities తో ఆ పైప్లో ఉన్న వాటర్ టర్బులెంట్గా మారిపోతుంది అని చెప్తున్నాడు. రైట్ నౌ the critical velocity r is equal to 2000 తీసుకుంటే what is the critical velocity for r? 2000. Now the solution, you know that r is equals to ud by v is equals to 2000. Now what is the thing you have to solve? You have to solve the u is equals to 2000 v by d. Now what is the diameter d? తీసుకున్నాం separate గా. So v is equals to, you know that mu is equals to p into v. So we have to calculate v is equals to mu by p, where mu is equals to 1.005 into 10 to the power of minus 3, p is equals to 9.2. So the value for this one is 1.07 into 10 to the power of minus 6 meters square per second. So distilled water is taken at 20 degrees. Okay, now what to solve? So మనకి 2 diameter pipes ఇచ్చారు. One diameter is 0.1 meter, other diameter is a 1 meter. Now taking 0.1 diameter pipe, substituting those formula, u is equals to, ఈ formula substitute చేస్తే u is equals to, what is the u? u is equals to 2000 into, what is the velocity? 1.007 into 10 to the power of minus 6 divided by 0.1 చేస్తే you are getting u is equals to 2 centimeters per second. Next, for 1 meter diameter pipe, what is the value of u? u is equals to 2000 into 1.007 into 10 to the power of minus 6 divided by d and the 1 meter. Then what is the value? u is equals to 2 mm per second. So that is the velocities of flows which will go in the different diameter pipes will become turbulent. Okay, so for 0.1 diameter pipe key, for 0.1 diameter pipe, the velocity is 2 centimeters per second. For 1 diameter pipe, the value is 2 mm per second. 2 mm per second. Next, category below. So in the initial slides we have discussed about the Reynolds number. Now we'll discuss about the Froude's number F. Then classification of flows according to the waste water surface behavior. Right, an important part of the base of classification of flow regime, the Froude's number F is equals to u by root of gd. So where g is acceleration due to gravity, where g is acceleration due to the gravity. Now when F is, we are calling them as a tranquil flow, subcritical flow, right? Okay, when F is less than 1, we are calling them as a tranquil flow. When F is equals to 1, we are calling them as a critical flow. When F is greater than 1, we are calling them as a supercritical flow or shooting flow. So what is the F here? F is a Froude's number. Initial case లో the flow of fluids గురించి Reynolds has given with the experiment RE. Now the second case with the Froude's number, scientist Froude has given some number F is equals to u by root GD, where G is equals to gravity, D is equal to diameter of the pipe. So here root GD is equals to, root of GD is equals to the celerity, the speed of propagation of the fluid of gravity waves on the water surface. When F is less than 1, U is less than root GD, then what we are calling this one as water surface waves will propagate upstream because they move faster than the current wave. Next, when F is greater than 1, U is greater than root GD. Here the water surface waves will be swept downstream because the current is moving faster than they can propagate upstream. In the sedimentology, the Froude's number is important to predict the type of bed form that will develop on the bed mobile sediment. So the Froude's number are generally used for the land beds. Land bed means the surface of the land, the sedimentology topic. So if you see whenever the water is generally, Froude's number దేని గురించి డిస్కస్ చేస్తుందంటే whenever the water is on the ground level, అంటే waters లో the rivers, ponds, lakes, in that type of situation the Froude's number is applicable. Now the C, when F is less than 1, When f is less than 1, what happens? The bed forms not in phase with the water surface. The bed forms are not in the phase with the water surface. Then f is less than 1, we are having the water baby is in this nature. Okay. Next, when f is greater than 1, the water surface, see the water surface, మనకి పైన చూడడానికి కాన్స్టెంట్ గా స్ట్రైట్ సర్ఫేస్, ఈవెన్ సర్ఫేస్, ప్యారలల్ గా వాటర్ డిస్టర్బ్ కాకుండా ఉంటుంది. అట్ ది సేమ్ టైం బెడ్ అనేది it is moving in the some wavy nature. Bed is moving in the wavy nature. When f is greater than 1, what happens here? The water surface అనేది it is having in the wavy nature. Thereby కింద f less than 1 లో ఏ మూమెంట్ అయితే, ఏ డిజైన్ అయితే ఉందో, ఏ మూమెంట్ అయితే ఉందో, f greater than 1 లో కూడా the same movement you can see on the top surface of the water. The bed forms are in phase with the water surface. ఇక్కడ ఏం జరిగింది? f less than 1 లో the bed forms are not in phase. The bed forms are not in the phase. Here the bed forms are in the phase. The bed forms are in the phase. Next one is the entrance region. Next topic is entrance region. When entrance regions means whenever the fluid is entering into the pipe, what's happening? What are the forces acting whenever the fluid is entering into the pipe? So in here, the thing to study is velocity boundary layer. Velocity boundary layer. The region of the flow in which the effects of viscous shearing forces caused by the fluid viscosity are felt. So what does this velocity boundary layer is saying? The region of the flow in which the effects of viscous shearing forces, caused by the fluid viscosity are felt. Next, second one, boundary layer region. The viscous effects and the velocity changes are significant. So what happens at the boundary layer region? Boundary layer and enti, for example, if you see this is a pipe. So the boundary layer and enti, this is a boundary layer. So the boundary layer of the pipe వచ్చేసి ఇది దీని లోపల వాటర్ ఉందనుకోండి, ఈ వాటర్ సర్ఫేస్ లేయర్ కూడా సేమ్ at this position. This is the boundary layer region where the viscous effects and the velocity changes are significant. Next, third one is core flow region, irrotational flow region. The frictional effects are negligible and the velocity remains essentially constant in the radial direction. So whenever the flow is flowing in a radial direction, whenever the flow of water is flowing in a radial direction in a pipe, the frictions effects are negligible and the velocity remains essentially constant. So whenever the flow is in radial direction, the velocity will be constant and the friction effects are negligible in the irrotational flow region. Okay. Now see the figure here, the development of velocity boundary layer in a pipe. The developed average velocity profile is parabolic and laminar flow, but sometimes flatter or further in turbulent flow. So if you see the graph between the velocity boundary layer, so see how the graphs are changing. So if this is a pipe, instead you're having a fluid, so this is x direction, this is the y direction, right? So this is center axis, Now see, whenever the water is flowing, the average velocity at the initial stage, so here the arrows shown are laminar, here the arrows shown are going in a pipe. The developed average velocity profiles are parabolic. So slowly, whatever the lines are passing in this direction, the hydrodynamic entrance region, right? So here the irrotational flow region, up to here irrotational flow region. Thereby what happens here? The flow is straight at this, up to this neck place, up to the x. So whenever it is changing the stage of irrotational flow region, it is converted into velocity boundary layer, which affects the shearing forces caused by fluid viscosity. So what happens slowly? These arrows are slowly getting changed to the parabolic form. See here how the shape is converted. Initially the line is in straight condition. Now it is making somewhat curvy nature, right? Next, third one. Third దానిలో ఏం జరిగింది? Here, the average flow of water fluid is making slowly it is converting into some bigger form of parabolic nature, right? Bigger form of parabolic nature. Again, this one is making somewhat extension, developing a velocity profile, So ila unna shape slowly it is converting to velocity profile, thereby the arrows are slowly disappearing at the boundaries and through the center it is emerging forward. So from this point to this point, it is hydrodynamic entrance region. ఒక స్టేజ్ దాటిన తర్వాత ఇట్ ఈస్ ఫుల్లీ డెవలప్డ్ హైడ్రోడైనమికల్ రీజియన్ అంటాం దీన్ని. అట్ దిస్ పాయింట్ ద టర్బులెంట్ అనేది స్టార్ట్ అవుతుంది. అంటే ఇది మీరు ఎగ్జాగరేట్ చేసి వెన్ ఎవర్ ద వాటర్ ఇస్ ఫ్లోయింగ్ త్రూ ఎ పైప్ ఆర్ వెన్ ఎవర్ యు ఆర్ dumping the water into the bucket or in a small channel, closed channel, you can see this type of observations, right? So the last stage of the observation is fully developed hydrodynamically developed region. Fully developed hydrodynamically developed region where it is converting into turbulent flow. Turbulent flow. So this is the entrance region of the fluid flowing in the pipe. Okay, right. Next, the hydrodynamic entrance region, the region from the pipe inlet, the region from the pipe inlet to the point at which the boundary layer merges at the center line. It is hydrodynamic entrance region. The hydrodynamic entrance length LH, the length of this region. So, ఏదైతే మనకి hydrodynamic entrance region ఉందో, that is nothing but the entry length LH. Next, hydrodynamically developing flow. The flow in the entrance region, this is the region where the velocity profile develops. సో ఎక్కడైతే మనకి డెవలప్ ఎక్కడ స్టార్ట్ అయింది, సో అట్ దిస్ పాయింట్ ఇట్ ఈస్ స్లోలీ కన్వర్టింగ్. ఈ పాయింట్ నుంచి ఈ పాయింట్ వరకు ఇట్ ఈస్ స్లోలీ డెవలపింగ్ ద షేప్ ఆఫ్ ద వాటర్. ఎస్. Next one, hydrodynamically fully developed region. So the region beyond the entrance region in which the velocity profile is fully developed and remains unchanged. Next, fully developed. When both the velocity profile, the normalized temperature profile remains unchanged. So where you are seeing here where it is fully developed and it is unchanged, fully developed hydrodynamically developed region. Next, the hydrodynamic fully developed is equals to dou u by r of x. R and ఏంటి y axis. ఇక్కడ r అని చూసారా, this one is a r, okay, this one is a x. Dou u by r into x by with respect to dou x is equal to 0, where u is equals to u into r. In the fully developed flow region of the pipe, the velocity profile does not change downstream, and thus the wall shear remains constant as well, right? See here the velocity profile does not changing with the downstream. So upstream means, so from here it is going to the other thing, so that's why it is a downstream. This side, this is a downstream. Okay, next one is the entry length for each type of flow, how it is formed. Now see the entry length. The hydrodynamically entry length is usually taken to be the distance from the pipe entrance to where the wall shear stress reaches within about 2% of fully developed value. Now see here, the pipes used in the practice are usually several times the length of the entrance region, and thus flow through pipes is often assumed to be fully developed for the entire length of the pipe. This simple approach gives reasonable results for long pipes, but sometimes poor results for the shorter ones. So whenever you are taking the physical member that is a pipe, whenever the pipes are of longer length, what happens? Whenever the pipes are of shorter length, what are the results they are giving? So whenever the hydrodynamic entry length for the laminar flow, we can write laminar flow, LH laminar head laminar flow by D is 0.05 Reynolds number, 0.05 Reynolds number, right? Whenever the hydrodynamic entry length for turbulent flow, LH into LH turbulent divided by D is equals to 1.359 1.359 RE into 1 by 4. 1 by 4. Next, if you take the hydrodynamic entry length for turbulent flow for an approximation, approximately it will be of up to 10, up to the value of 10. So this will be used for the solving of the problems. Okay. Next topic is Reynolds experiment. Next one is a Reynolds experiment. How does the Reynolds have made an experiment for conducting the water flows in the pipe? So the real behavior of the fluids, flowing in a pipe, well described by an experiment carried by Mr. Reynolds in year 1883. సో మనం ఇప్పుడు చెప్పుకునే కాన్సెప్ట్ నాట్ ఇట్ ఈస్ వెరీ నాట్ ఓల్డ్ వన్, ఇట్ ఈస్ వెరీ 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 ఓల్డ్ టాపిక్. ఏ ఇయర్లో నవ్ వీఆర్ ఇన్ ద 2020, వీఆర్ ఇన్ 2020. రైనల్స్ అన్నాడు ఎప్పుడు చేశాడు దీన్ని? 1800 టైంలో చేశాడు. మీన్స్ 1800, 1900, 2000. సో ఆల్మోస్ట్ మెనీ డికేడ్స్ బ్యాక్ రైనల్స్ అనే సైంటిస్ట్ హ్యావ్ క్యారీడ్ దిస్ ఎక్స్పెరిమెంట్. సో కొన్ని వందల ఏళ్ళ తర్వాత మీకు ఇప్పుడు ఇది సెకండ్ ఇయర్ సివిల్లో మీరు తెలుసుకుంటున్నారు. See how old type of concept you are learning, but it is a basic introductory those who are studying the fluid mechanics. Okay, he set up the following apparatus. So conduct cheyadaniki the flow yokka behavior, the fluids yokka behavior ela jarugutundi real time lo telusukodaniki Reynolds has made an experiment in 1883. So daniki kavalsina setup chesadu. What is here? He has a container lo he is having a water, right? So in the container he made an orifice, a jet, so a glass tube, a transparent glass tube for vision, for visual, and also he is having a valve at the bottom, and the water biting, the dye biting is having a valve at the bottom. He took a dye, some pigment, right? The discharge is controlled by the valve on the small, the discharge is controlled by the valve on the small filament of a dye. So the discharge ఎలా కంట్రోల్ అవుతుంది? డిశ్చార్జ్ అంటే బయటకు వచ్చేది కదా. The discharge is controlled by the valve. See, this is the valve opening and closing, and a small filament of dye. And a small filament of dye indicates the behavior of the flow. By changing the Reynolds, by changing the flow, Reynolds noticed what? See, so what does the apparatus consist of? The apparatus has a tank having water with constant head. Okay, a tank having the water with constant head. So I see here a tank having the water with constant head, and constant water head level should be constant. Second one, a small tank containing some dye. So see the figure here. This is a small tank. A tank లోపల ఇంకొక చిన్న setup ఉంది where you are having a dye. It may be red color, blue color, yellow color, any color of dye. Next, a glass tube having bell-mouthed entrance at one end and regulating valve at the other end. So what is the next thing you are having? You are having a glass tube with a bell mouth opening, bell mouth laga undi, other end వచ్చేసి elbow వేసుకొని you are having a valve opening at the other end which is outside the container. Now the water from the tank, ఏం జరుగుతుంది? The water from the tank was allowed to flow through the glass tube. The water from the tank was allowed to flow through the glass tube. The velocity of flow was varied by regulating valve. So water container water is flowing through the glass tube. Okay, so and it is controlled with the valve which is placed outside. A liquid dye having some same specific weight of water was introduced into the glass tube as shown. So తర్వాత ఏం చేస్తున్నాం? Whenever the water is flowing through the glass tube, we are also sending a dye through the jet of orifice through the glass tube along with the water. Now what's the changes you are observing? At low flows, at low velocities, the filament remained intact and almost straight. This type of flow is nothing but laminar flow, and the experiment look like in this manner. So మనం గ్లాస్ ట్యూబ్ ని మనం ఎగ్జాగరేట్ చేసుకుంటే ఈ పాయింట్ మనము పెద్ద చేసుకొని చూద్దాం. ఎగ్జాగరేషన్ మీన్స్ లుకింగ్ in a bigger size. సో ఇది వాటర్ అనుకుంటే హియర్ ద డై అనేది స్ట్రైట్ లైన్ ఫ్యాషన్లో ముందుకెళ్తుంది. When at higher levels, at higher flows, the filament began to oscillate. So whenever the velocity, whenever the discharge, medium discharge లో జరుగుతున్నప్పుడు, right, what happens, the filament flow, the dye అనేది began to మెల్లిగా ఒక స్లోగా ఇంత దూరం వచ్చిన తర్వాత స్లోలీ ఒక స్ట్రైట్ లైన్ ఫ్యాషన్ తీసుకున్న తర్వాత slowly it begins to oscillate. This type is known as transition flow, and the experiment is looking like this. Next, last లో for even higher flows, ఇంకొంచెం ఎక్కువ velocity flow జరిగినప్పుడు the filament is found to break up and completely gets diffused over the full cross section. సో ఎప్పుడైతే హయ్యర్ వెలాసిటీస్ మనం డిశ్చార్జ్ చేస్తున్నామో వాట్ హ్యాపెన్స్, స్టడీగా ఉన్న లైను చేంజ్ అయిపోయి ఆసిలేట్ అయిన తర్వాత ఆటోమేటిక్గా అది తర్వాత ఏమైంది, డిస్పర్స్ అయ్యేసి వాటర్ మొత్తము డిస్ట్రిబ్యూట్ అయిపోయింది, రైట్. వాటర్ మొత్తం డిస్ట్రిబ్యూట్ అయిపోయి it is mixed with water and coming in the turbulent flow. So this type of experiment is done by the Reynolds in 1883 itself and shows the real behavior of the fluid. Understood? Yes. So with this, what he concluded, Reynolds experimented with different fluids. So ఏం చేశాడు, ఇలాంటిది డిఫరెంట్ ఫ్లూయిడ్స్తో ఆయిల్స్ లోపల మళ్ళీ రకాల కిరోసిన్, పెట్రోల్, డీజిల్ అండ్ అదర్ టైప్ ఆఫ్ క్రూడ్ అండ్ అదర్ టైప్ ఆఫ్ వెజిటబుల్ ఆయిల్స్ ఇవన్నీ చూసుకొని డిఫరెంట్ పైప్స్ అండ్ వెలాసిటీస్తో టెస్ట్ చేసి ఫైనల్గా ఏం చెప్పాడు, ఎవెన్చువల్లీ హీ ఫౌండ్ దట్ ద ఫాలోయింగ్ ఎక్స్ప్రెషన్ ఇస్ ప్రిడిక్టెడ్ which type of flow was found. RE is equals to rho into V into L by mu, in which RE is the Reynolds number, rho is the fluid density, V is the average velocity by the characteristic length of the system, right, and mu is a fluid viscosity. Then the Reynolds number is the ration of forces and hence has no units. So the ration of forces kabatti it doesn't have the units. Therefore flow in the pipes normally confirm the following: RE greater than less than 2000 annappudu it is giving a laminar flow. When RE is in between 2000 to 4000, we are calling them as a transition flow. When RE is 4000, we are calling them as a turbulent flow. So based on this, these values are only a rough guide, however. So ఈ values అనేది జస్ట్ మనకు ఒక ఇండికేషన్ మాత్రమే. Laminar flows been found at Reynolds number 4000 also. ఇంకొన్ని ఎక్స్పెరిమెంట్స్ కొన్ని టెస్ట్లలో లామినార్ ఫ్లో ముందు మనం ఏం చెప్పుకున్నాము, లెస్ దెన్ 2000 చెప్పుకున్నాం. బట్ ఇన్ సమ్ కేసెస్ ఇట్ ఈస్ బియాండ్ 4000 అని చెప్తున్నాడు. ఫర్ ఎగ్జాంపుల్, ఇఫ్ యూ కన్సిడర్ ఏ గార్డెన్ హోస్ ఆఫ్ 15 mm diameter pipe. అంటే ఒక గార్డెన్ లో హోస్ పైప్ ఉంది, అది వచ్చేసి 15 mm diameter. దెన్ ద లిమిటింగ్ యావరేజ్ వెలాసిటీ ఆఫ్ ద లామినార్ ఫ్లో ఈస్, సో ఇది చెప్పాడు 15, రైట్. సో RE ఈజ్ ఈక్వల్స్ టు ఫార్ములా అప్లై చేసి, సో RE ఈజ్ ఈక్వల్స్ టు 2000 పెట్టుకుంటే 2000 rho ఈజ్ ఈక్వల్స్ టు 10⁻³ V, L ఈజ్ ఈక్వల్స్ టు 0.015, right, divided by mu is equals to 0.55. These are the standards into 10⁻³ Therefore V is equals to 0.073. So this is very low. The number is very low flow, and hence we can see that in the most applications we deal with the turbulent flow. The velocity below which there is no turbulence is called the critical velocity. It's called as, so whenever there is no turbulent flow, appudu aa velocity ఏమంటాం మనము critical velocity అని చెప్తాము. Critical velocity అని we will say. Understood? Okay, so the time is also very less than 1 minute. So here we'll stop the class. Very few were present: RAJESH.K, Sandeep, and Gogin and Raviteja. So once the video is uploaded in the YouTube, I'll forward the link to your group. Open it, wave it, and share it. Okay, na? Those who are not in the class, share this link personally to their WhatsApp. Okay, so we'll continue the class in the next video, that is in the lecture 29. Thanks for watching the video. Right, so tomorrow